guys, today we're going to be talking about continuity and determining whether a function is continuous at a certain point or not. So to determine whether a function is continuous or not at a certain point, there's certain things that must be true. So for a function to be continuous, first of all, the function must be defined at that x value. So f of a must equal some value, so we'll say that some value is x, and then after that the next thing that must be true is the left hand side limit must equal the right hand side limit, or meaning that these two values from the left and right hand side must be approaching the same thing. So since this is calculus, we're just going to say that the limit as x approaches a must exist, so it must be true. So the limit as x approaches a must exist, and then after we prove that that left hand limit and right hand limit is equal to each other and that limit exists, the last step that must be true is that that limit that we said that exists must equal whatever we say that it's defined as. So f of a equals x, or it must be defined. So let's make sure we put that out there, must be defined. So it must have some type of output at that point. And then the left hand and right hand limit must exist or must equal each other, telling me that the limit exists. And then the last step is that whatever we say that the limit is equal to must equal what we said it was defined at. And at any point that it fails, we can say that it's not continuous, because all of these have to be true for a function to be continuous. So if the first step we test is that it must be defined, and the function that we're given is not defined at the point that we're looking to determine if it's continuous or not, then just stop there. It's not possible for it to be continuous if it fails any of these steps. So let me give us an example of a problem, and let's consider if it's continuous or not at a certain point. So let me give you a piecewise function. So we've got this piecewise function. We'll call it some quadratic here, and we'll give it a restriction when x is, let's just say, less than -2. And then another piece of this function, let's just say -2x squared minus x plus 4. And we'll say when x is greater than or equal to -2. Okay, so to go through our steps, we're going to have to see, is this function continuous? We're going to ask, is it continuous at x equals -2? Okay, and then we're also going to see, is this function continuous at x equals +2? So this will be part A for us, and this will be part B. So this will answer a few questions just using the same function. So the first test, let's do A. Let's determine, is it continuous at x equals -2? Well, since it's a piecewise function, we have to look at our restrictions. And we can see here that -2 is actually being told that it's x is greater than or equal, so there it says equal to -2 with our second piece. So we do know it's defined, so let's show that this f of x function, f of x, or f of -2, is actually defined, and see what it's defined as. So that would be -2 times -2 squared minus a -2 plus 4. Okay, so whatever that gives us is what our f of -2 will be defined as. So that would be -2 times 4 plus 2 plus 4. So -2 times 4 is -8. -8 plus 2 is -6. -6 plus 4 is -2. Okay, so we know that f of -2 is defined as -2. All right, so now the next thing I need to do after that was to see if the limit exists. So to see if the limit exists, we need to make sure that the left-hand limit is actually equal to the right-hand limit. So let's evaluate the limit as x approaches negative 2 from the left-hand side. Well, to approach it from the left-hand side, I need to use the top equation. So I'm going to take this negative 2 and I'm going to plug it into the top equation, which will equal negative 2 squared minus a negative 2 minus 8. Alright, so when I evaluate that, that would be 4 plus 2 minus 8, which gives me 6. 4 plus 2 is 6. 6 minus 8 is negative 2. So, as I look at this, I can see that I've got a value that it's defined at that's equal to my left-hand limit. So far we're good. Now I need to check the right-hand limit. Well, the right-hand limit is nothing more than what we've already evaluated for this function to be defined as. So I'm just going to use this and go ahead and carry it all the way down here, which we found is negative 2. So as I can see, my left-hand limit is equal to my right-hand limit. And since that is true, then the limit exists. So the last step that we need to check is we need to see, does the limit equal the value it's defined as? And since they both equal negative 2, I can say that this is continuous at this piece. So yes, it is a continuous function at x equals negative 2. So now when I scroll back up here and we use part B, we want to see, is part B continuous at x equals negative 2? Well, this is actually a little bit easier because it's not part of our restrictions in our piecewise function. So all I have to do really is check and make sure that x equals 2 is in the domain of this function. So this says x is greater than or equal to negative 2. Therefore, x equals 2 will be a part of this second piece. So let's see, what is it defined as? F of 2 will equal negative 2 times 2 squared minus 2 plus 4. Okay, so when I write this, I would end up with negative 2 times 4, which is negative 8 minus 2 plus 4. So the value that it's going to be defined as is equal to negative 8 minus 2, which is negative 10. Negative 10 plus 4 is 6. Okay, so since this is calculus, I'm going to state a few things that's going to allow us to know that this is continuous. First of all, this is a continuous function. This is the piece we're dealing with. This x minus, this negative 2 x squared minus x plus 4 is a quadratic, which is a continuous function. So since it's a continuous function, we know that it will be continuous from the interval x is greater than or equal to negative 2. So I can make the assumption that it would be continuous.